Today, I like to teach about robotics and its applications. Unit of localization, and mapping. Robots determine their position in an environment, and simultaneous localization and mapping uses sensors like cameras, lidar, and IMUs. So, self-localization and mapping is referred to the ability of a robot to determine its position in an environment while simultaneously creating a map of that environment. This is commonly known as simultaneization and mapping. Key concepts: self-localization. The robot's estimates its position based on sensor data. Methods include photometry, GPS, LiDAR, and vision-based techniques. Mapping: the robot builds a representation of its surroundings. Techniques include grid-based maps and feature-based maps. Challenges: sensor noise and environmental uncertainties, dynamic obstacles affecting localization accuracy, high computational requirements for real-time processing. Applications: autonomous vehicles and robotics, navigation, indoor mapping, and exploration. These concepts play a vital role in robotics and artificial intelligence, enabling machines to navigate and interact with the world effectively. That is the challenges in localization. Localization is crucial for autonomous robots, but several challenges can affect accuracy and reliability. Sensor like LiDAR, cameras, and GPS can have errors due to environmental factors. Measurement inaccuracies lead to incorrect position estimation. Sensor data uncertainty and noise, such as LiDAR and GPS, that is, the measurement inaccuracies lead to incorrect estimation. Dynamic environmental changes. This is the second one. Dynamic environments mapping. Example for people, vehicles create difficulties in mapping and localization. The robot must constantly update its position and to adapt. Data association issues, that is the difficulty in distinguishing between similar landmarks. Misidentifications of objects leads to localization errors. Computational complexity, that is a real-time localization requires high processing power. Complex algorithm like simultaneous localization and mapping demand significant resources. Sensor localizations, GPS signals can be blocked indoors or in tunnels. Camera struggles in low light or foggy conditions. Accumulations of errors, small errors in positions estimates add up over time. Recording and odometry often suffer from accumulative inaccuracies. Vision-based localization uses cameras and image processing integrated with AI, artificial intelligence, and deep learning, challenges lighting, variations, and applications. So, vision-based localization uses cameras and images processing techniques to determine a robot's position in an environment. It's widely used in robotics, autonomous vehicles, and augmented reality systems. The working principles of vision-based localization is cameras capture images or videos of the surroundings. Computer vision algorithms analyze visual features like images, textures, objects. Position estimation is done using techniques like feature matching and optical flow and deep learning based sense recognition. Types of vision-based localization: monocular localization and stereo vision. So here the two types of localization is there. Stereo vision uses two cameras to calculate path information. So visual based localization uses cameras and image processing techniques to determine a robot position. This is the advantage of user-based localization provides rich environment data compared to traditional sensors works well in GPS environments, indoor tunnels, caves can recognize objects and landmarks for precise localization. Challenges and the limitations of vision-based localization lighting conditions. Performance can be affected by low light, shadows, or glare. Computation complexity requires high processing power of for real-time localization. Calculations and applications, autonomous vehicles, self-driving cars use vision-based localization for navigation and augmented reality. That is called AR. AR applications track user movements in a real-world environments. Industrial robotics used in warehouses for factories for object recognition and navigation. Vision-based localization is a powerful technique for accurate positioning and navigation, but it requires high computational power and environmental conditions for the best results. Ultrasonic based localization uses ultrasonic sensors for distance measurement, works well indoor environments, limited range due to signal reflections. That is the ultrasonic based localization uses ultrasonic sound waves to determine the position of a robot or object in an environment. It's commonly used in indoor navigation obstacles detection and robot applications. It is a working principles of ultrasonic based localizations, high frequency sound waves. The advantages of ultrasonic based localization is inexpensive and widely available and simple and reliable, easy to implement for indoor positioning, works in dark environments, unlike vision based localization. Electronic sensors do not rely on light. Adults and the limitation range work based within a few meters, not suitable for large spaces. Interference reflections from the multiple surfaces can cause refers that is the errors in position estimation are based within a few meters, not suitable for large spaces. Interference reflections from the multiple surfaces can cause refers that is the errors in position estimation. Ultrasonic based localizations of applications, that is the autonomous robots used for indoor navigation and obstacle avoidance, medical applications using ultrasonic imaging diagnostics, security systems, motion detection and in alarm system, information, position tracking, etc. Ultrasonic based localization is cost effective and a reliable technique for short range navigation, but it faces challenges with the accuracy and an environmental experience. So the introduction of GPS, that is the global positioning system localization, a satellite based navigation system that is the precise location of an object or an air. It's widely used into navigation, autonomous vehicles, and geolocation services. Working principles of ultrasonic-based localization: GPS receives communicate with at least four satellites to calculate position using penetrations and the infrastructure needed, unlike IR, infrared or ultrasonic localization and additional hardware is required. So challenges and limitations of ultrasonic based localization: GPS signals are weakly inside the building and underground. Weather and environmental effects. High clouds, tall buildings, or forests can reduce accuracy, power consumption. GPS receivers consume a significant power, making them less ideal from smart devices, signal delay, and errors. Here, the atmosphere conditions and satellite clock errors can affect accuracy. That is the main application of ultrasonic localization. Use of ultrasonic localization here used for navigation in self-driving cars, drone and robots, geolocation services used in mobile phones for maps and tracking. And here the ultrasonic based localization using in agriculture, disaster management, GPS localization here in the agriculture helps in precision farming, automated missionary navigation, disaster management used for search and rescue operations and emergency response. GPS localization is a powerful and widely used technology for outdoor positioning. Its visibility and is less effective for indoor navigation. Thank you very much. Thanks.